Today we are going to study about ballistic transport in quantum nanowires. So first of all, let's make a comparison of what a quantum wire is and what a bulk wire is. So if we know that if the radius of the wire is very greater than the de Broglie wavelength of the electron, it will be considered as a bulk material. While if the radius is of the order of the de Broglie wavelength of the electron, it is a quantum wire. Here we are taking an additional condition of mean free path. So length of the wire is very less than the mean free path of the electron, while it is bulk if the length is very greater than the mean free path. So first of all, what is mean free path? So you see that here the electron is traveling from one point to the other, gets collides and then deviates and then collides and then deviates in another direction. So what we can do is we can find out the time period it takes to move from one after the collision to before the collision, and then for the next collision, and then for the next collision. Find the distance traveled for each of these and we'll find, and then take a mean of them, will give you the mean free path. And similarly, the relaxation time can also be found like this. It is just the average time of each of these paths. That will be the relaxation time. So if we are considering a bulk wire, you see that we have just studied about Root's model, and we see that there will be a lot of scattering. Electron will collide with the lattice points, ions, and all the electrons will be contributing to conduction, and positive ions will be present in a sea of electrons, and these electrons will collide with these ions. While in a quantum wire, they will be, because it is less than the mean free path, it means that when it is colliding, so suppose that if it is colliding from here to here, so the length is less than this, so it means it will not be able to collide with anything at all. So that is why there will be no scattering at all. This is an ideal case. So this is another difference. So because we know that radius is given by resistivity length upon the cross-sectional area, so the conductance will be given by 1 upon g is equal to rho L upon A. So we see that if for a bulk material, as the area, cross-sectional area of the wire will increase, the conductance should ideally increase. So this is what we should expect. But in actual, we see that in a nanowire, where the length is less than the mean free path, although the conductance will increase, but it will increase in definite steps. It will be quantized. So that is why conductance will be quantized in for ballistic transport. And we call it ballistic because it moves without scattering. The electron will move from source to the drain without any scattering, and that is why it is a ballistic transport. So in Root model we have considered, so in order to explain this phenomena, we'll have to understand, we will not be able to explain it with Root's model. We'll have to explain Fermi gas model for the conduction of the electron. So Root's model is a classical model, while Fermi gas model, although is a quantum mechanical model, but it is semi-classical model. It means that some of the concept of classical physics will be used in this model as well. So in Root's model, we have seen the total velocity will be equal to the thermal velocity plus the drift velocity. But in Fermi gas model, we'll have to replace thermal velocity with the Fermi velocity. So we'll have to take care of the Fermi velocity of the electrons. So the question arises, what is Fermi velocity? So you see that in a metal, the highest energy electrons are actually Fermi electrons, and the velocity associated with them will be the Fermi velocity. So if we have to draw in a K space, so first of all, we know how we go from real space to K space. So if interatomic distance or interplanar distance in real space is A, then in K space, distance between 2 points will be pi upon A. If it is a square lattice, perfectly square lattice. And it will follow this equation where Fermi energy will be given by h bar square k square upon 2me. So in K space, equal energy surface will give you the maximum equal energy surface will give you the Fermi energy, and the magnitude of it in terms of K will be Kf. So from here we can find the Fermi energy and the corresponding Fermi velocity. So the maximum energy electrons will have Fermi velocity. So in Root model, we have considered that all electrons contribute to conduction, but in Fermi gas model, it is all electrons cannot contribute because the bound electrons are not moving. Only the electrons, the valence electrons are moving. So only the Fermi electrons contribute to conduction. In Root model, we have considered the particle nature of electron, but in Fermi gas model, it will be the wave nature of electron that we will have to consider. So we can talk about K space, and we can say that okay, the maximum energy electrons will be Fermi energy, and the wave vector associated with it will be Kf. While we can also transfer it to momentum space. We can represent the lattice in momentum space also, and we can convert from K space to momentum space by using this relation, which is P is equal to H bar K. So if it is a circle in K space, it will also be a circle in momentum space. So let's try to understand it furthermore. So this we have already explained that the difference between Root model and Fermi gas model. Now we have seen that if it is a quantum wire, then it will have this circle which will represent a equal energy contour in momentum space. If it is a two-dimensional material, but because we are considering a wire, it will also have some amount of thickness, so we can consider this as a circle. So we see that if there is no electric field, then this sphere will be such that it will have equal number of negative momentum vectors as compared to positive momentum vectors, and that is where total net momentum will be 0. But if electric field is applied, then this Fermi surface will shift in a particular direction, and that will happen when the electric field is not equal to 0. So this is how we represent the motion of electron in momentum space. So here this is what we are discussing here, that because all the electrons will be moving randomly in all the possible directions, and therefore the net movement of the electron will be 0. And when electric field is applied, then net momentum will not be equal to 0. And drift velocity will be similar. Here also we have shown that drift velocity is QE tau upon ME. Similarly, in Root model also we have seen this. While in Fermi gas model also, this will be the drift velocity that we will be using. So momentum, as we know, is given by H bar Kf, where Kf can be found by this relation. This we have also done in density of states, so you can also check it, that we can find out the total volume occupied by one state, 1 upon 8 because we don't want to count the states again and again, and twice because each electron can have 2 spins. That is why. So because of it, the Fermi velocity will be given by this relation. And so in order to get just an idea of the magnitude of this Fermi velocity, we see that Fermi velocity is of the order of 10 to the power 6 meters per second, and it is very, very greater than the drift velocity. Okay. So the amount of shift in the momentum space, the momentum sphere, will be given by this. So this we have found out simply by using force as ma. So m will be the effective mass into d upon dt of the drift velocity, and it can also be written as dp upon dt, and because m we can take inside, because m is a constant quantity, it will not change anything, and p is h bar k, and so force will be equal to QE because the electric field is being applied. So from here we can find out that change in momentum will be QE tau into E vector, and tau is the relaxation time that we have already discussed. So it means the total velocity will be a Fermi velocity into the drift velocity. So the mean free path then we can find out by multiplying velocity into the relaxation time. So we find out that the mean free path for copper, when we consider the Fermi velocity, is actually 100 times the lattice constant. It means that electrons rarely scatter with the lattice, and they don't scatter with the lattice. They scatter only with lattice imperfections and phonons. On the other hand, classically we see that if we consider thermal velocity, because drift velocity is anyways very smaller as compared to Fermi velocity, and here also it is very small as compared to thermal velocity, we'll see that the mean free path will come out to be around 10 to the power minus 9 meters, which is 8 times the lattice constant. So here still there is probability of collisions, but when we see quantum mechanically, we see that there are no collisions. If there are no lattice imperfections, there will be no collisions. This we can understood very nicely in chronic Penne model also. So you can also check chronic Penne model where block waves are discussed, and it is also discussed that when we are shifting from a free electron to a periodic potential, electron in a periodic potential, that only effective mass will replace the mass, and rest everything else will remain the same. It means that electron will behave as if it is free with a few differences. Okay, so and this we saw that if we consider Fermi velocity, then we see that mean free path is very large. But now if we consider low temperature, then we see that the mean free path is yet larger. So it is of the order of 0.003 meters, which is very, very large as compared to the one which we discussed earlier at room temperature. So it is 8 millionth of the lattice constant. So it means that, as we are discussing, that the electron will, in a periodic potential, the electron will move and it will behave as if it is free. The only difference being that the free electron mass will be changed by the effective mass. So let's also discuss that how resistance and conductance will be classically. So we know that resistance is given by V upon I, and these relations are very commonly known because it is just change in potential is integral of electric field, dot product of integral of electric field and the length vector, while current is actually surface integral and current density into area vector. So this is how we can derive it. So resistance can be written as this. Actually directly we could have written, so it would have been R is equal to rho L upon A. So rho is conductivity, resistivity, 1 upon sigma will be conductivity. Therefore resistance is 1 upon conductivity, length upon the cross sectional area. But for a two-dimensional case, we'll have only a width of the material, will not have any height, so it will be, area can be replaced by just width. While for a one-dimensional material, it is an ideal case where say it is just a line, so we can say that resistance will be L upon sigma. So these conductivities, they will have different units for each of these relations. So this will be for the volume, this will be for an area, while this one will be for line. So sigma has different units in different dimensions. So if we use this relation which we have derived for bulk, we see that it depends linearly on length and inversely on area. So as the radius, as this is length actually, A is actually length. So as the length of the material no, this is the cross-sectional area. So this we can write as capital A, or only one length actually. So we'll have to take A square for it. So if you have to talk about area, we'll have to take A square. So this should be squared, and this also has to be squared, and this also has to be squared. So this is the cross-sectional area, and we use this relation. Then we see that resistance will be of the order of 10 to the power 5 minus 5 ohms per meter. While if this is the cross-sectional area, 10 micrometer squared, then it will be 53.95 ohm per meter. And if it is 10 nanometer, it will be this. But you see that as we go to smaller and smaller dimensions, this will not work, and we'll have to take care of other factors also. So if we reduce the area from micrometer to nanometer, from 80 to 100 nanometers, and if in this region there will be radius dependence of the conductivity, while if we go yet further, then it will be a quantum wire. because then quantum mechanical effects will be prevalent. Otherwise here it is just because it is not of the order of the cross-sectional area is not of the order of the area which we will get if we use de Broglie wavelength as the radius. So that is why um, uh, here it will be radius dependent. So by this model we can explain it, where we'll have to take care of other scattering phenomena like grain boundaries and wire surface will become more prominent. Okay, so now directly we'll come to ballistic transport, where we see that we have been discussing about it, that if the length is less than mean free path, but then we are considering two kinds of collisions here. One is elastic collision and the other one is inelastic collision. So everybody knows this very well, that in elastic collision there is no change in energy, and electrons and whatever collisions will be there will be with the fixed impurities and electrons. While in inelastic collision, dephasing events will take place. So dephasing event means that the phase coherence will be lost, because we are considering the wave nature of the electron. So it will have some phase with which it will be moving through the lattice. If it is an elastic collision, it will never lose its phase. While if it is inelastic collision, and the collision will be with phonons and it will lose its phase, and sometimes that is a very unpleasant situation which is not required. So the mean free path for elastic collision will be depicted by Lm, and for inelastic collision it will be L5. So it is also called phase coherence length, and this length is also very important, and it is of the order of 10 to 100 nanometers at low temperatures. So So in the first case that we have discussed, it was a classical transport when L is very greater than both of these mean free paths. But if it is less than mean free path and less than the elastic collision and inelastic collision mean free paths, it will be ballistic transport. It will be a coherent transport. Electron travels like a bullet without hitting anything. And in this case, Schrodinger's equation can be used and it can be solved. So now let's understand what we mean by ballistic transport, and let us try to understand it further. So let's say that we have because if this is our channel which has a radius of the order of de Broglie wavelength, and then in order to provide current to this channel we'll have to use some cables, wires, and so we are considering these wires, and then we'll have to use a source, potential source. So we are considering these wires as bulk materials. They are actually bulk materials and they are in contact with our nanowire. And we consider them as reservoir of electrons. So for these reservoirs of electrons, these are nothing but wires. So if we have this as a quantum wire, so we'll have to use these thicker wires. If I have to draw it, let me just... So as compared to our nanowire, these wires will actually be very thick. So it will be, you also require some resistor here, but just to explain. So this is a situation like this. You have a potential difference, you have a quantum wire, and you have these thick wires. And these thick wires are being considered as reservoirs of electrons. So for these reservoirs also, it is very important to understand how the energy levels will be. So we can use h bar square k square upon 2 me star and consider these reservoirs as, because their dimensions will be in millimeters, micrometers, so they are put a particle in a well with large thickness. So if D is very large, then the difference between energy levels will be very small. So it will be continuum of states. So this will act like a bulk material because it is a bulk material. So it will have infinite number of energy levels. So the source and the sink actually has a large number of energy levels, while the wire will have discrete energy levels. And we have found earlier also that the energy for a quantum wire is given by h bar square k square upon 2m, while k we know in two directions it will be quantized and in one direction it will be continuous. So in the x direction it will be continuous and in y and z direction it will be quantized. So this quantized energy we can take separately and we can find out what is the difference in energy levels energy subbands, because in these wires you'll have those subbands. If you remember, just check a density of state lecture, and you'll know that you'll have these subbands, these parabolas actually. So this is what we're talking about. So this continuum of states will be because of the motion in kx direction, in x direction, and in the other two direction the energy will be quantized. So these energy levels will be E, N, Y, and Z. And we can find out the difference between these energy levels. Okay, so now if the width of these, if the width and the height of these wire is same, so we can get this. And so if we use the maximum energy, which is the Fermi energy, that will give you the maximum, that will give you the number of states that will be possible in the inside the Fermi surface. So all the k values that will be permitted will be given by this n actually, capital N. So you see that when we are increasing in energy, so if it is E1 it will be first state, if it is E2 it will be the second state. Similarly, if it will be EF maximum, so it will be giving you the total number of states. So the total number of modes or states, because we can also call it modes, because it is it will be like a standing wave kind of a situation. So the number of modes possible will be given by capital N. So here we can take W upon H bar pi outside and replace 2MEF by this relation, which will be given by 2 pi upon K will be 2 pi upon lambda F. We can replace it here. So you can replace all these things and this is what you get. So you see that number of modes will depend upon the thickness of the wire and the Fermi wavelength of the electron. So when the thickness of the wire will increase, so whenever it will be of the order of lambda F upon 2, you will have one mode can increase. Otherwise, if suppose it is half of it, half of the thickness is almost half of the wavelength or 1/4 of the wavelength, so it will not be the complete mode. So you require this W to be such that it is a multiple of lambda F, Fermi wavelength upon 2. So here we are considering Fermi wavelength because the maximum energy electron de Broglie wavelength will be actually the Fermi wavelength. So as W will increase, number of channels will also increase, and each time the thickness is of the order of lambda F upon 2, a new channel is added. So it means that it will be discrete. So thickness, if it is increases in discrete manner, additional channels will be added. So when we calculate the resistance for such a channel and conductance for such a channel, we see that the conductance is also quantized, and we see that conductance will be given by 2e square upon h bar into n. So 2e square upon h upon into n. So n will be the number of conduction channels, and n we can replace from here, which is w upon lambda f upon 2. So it will be 2e square upon h and this. So from here we can also find out resistance. So for the first channel it will be h upon 2e square. So this is called resistance quantum. Similarly, 2e square upon h, the minimum number which is available for conductance, will be the conductance quantum, and for the resistance it will be the resistance quantum. And subsequently, as n will increase, g will also increase, multiple of 2e square upon h, and r will decrease by h upon e square. So conductance is given by 2e square upon h into n, and resistance is given by h upon 2e square into n. So we see that conductance and resistance, both of them will be quantized, and the quantization factor will be 2e square upon h. And so here we can, if we plot it, we'll get something like a step function, which we have already discussed. And if you want, you can also draw it. So it will be something like this. Maybe I have it here. Yeah. So it will be like this. So you see that this will always be a multiple of 2e square upon h. So it will be it is conductance actually. So area will be W. So here it will be 2 e square upon h, and here it will be 2 e square. Um, so 2 into 2 e square upon h, and then it will be 3 e square upon h, and so on. So it will be a step function. So now we have understood that conductance is quantized. Although we see that conductance will be increasing in case of bulk material also. So if in bulk area will increase, the conductance will increase. And similar is the situation in quantum wire also. But the only difference being that in this case, in bulk material, it will be a linear increase will be linear, while in a quantum channel it will be a quantized increase. It will be in steps, multiple of 2 e square upon h. So now let's take an example of a field effect transistor, and let's see that how conductance will change.